This is the CRABLab at the Georgia Institute of Technology. It's called that, in part, because they study crabs here.
One of our most high-tech experiments is we take these ghost crabs and we bond strain gauges, little devices which measure bending and buckling to their limbs. And the strain in their limbs tends to increase as the animals run around on different sorts of materials. So we can take images of animals running around at over 1,000 frames a second. We can slow that down and we can look very carefully at how a limb is moving or how a foot is entering the material.
Animal motion fascinates physicist Daniel Goldman, but what he's really interested in are the granular materials they run on, like the sand. He wants to discover the physics of granular flow.
It turns out that the flow of materials like sand can behave like fluids and solids and gases all in the same flow, and this is still not understood in the way that physicists and engineers like to understand these sorts of things, by writing down equations.
By experimenting with models, animals,
that was pretty good,
and robots, Daniel's team is building equations that explain the physics of granular flow.
The practical considerations are that the understanding the physics gives us some way to understand the forces generated on feet of running organisms or running robots when they have to run over this complicated shifting material.
Daniel's students have studied sea turtles on beaches in the wild and cockroaches in the lab. The trick is getting the animals to walk in the right direction so their motion can be picked up by high-speed cameras. Though animal experiments reveal some clues about granular flow, Daniel uses models to more accurately measure the force of a footfall.
We use a robot arm to maneuver sort of feet-shaped objects into a model granular material, a collection of 6mm BBs. And that's the foot, and that we can sort of change the geometry of the foot and see how different geometries and different penetration profiles create force. The other physical model is one which is sort of closer to the organism, is a multi-legged physical model, a robot we call Sandbot. And Sandbot has very simple feet, but very simple feet whose trajectories we can control carefully. And we study the motion of the robot and the penetration, the forces developed by penetration on those feet as it moves into different granular materials, different sand.
The granular material in this experiment is 90 kilos of poppy seeds. After each run of the robot, the poppy seeds need to be mixed up by blowing air, supplied by multiple leaf blowers. This is because footprints create patterns deep in the sand. Daniel's students have modeled it.
That's the first strike of the foot.
The black lines are stress lines, granules lining up.
The history of the material plays a role in the strength and the properties of the material. And the air blows the poppy seeds up and creates what's called a fluidized state. And creating that fluidized state, we then turn off the air, the grains settle into a loosely packed state, and by pulsing air to that fluidized bed, we can tightly pack the material, which we can then allow the robot to run around on. And we're interested to see how the preparation of the granular material affects the locomotion.
Sandbot was designed by researchers at the University of Pennsylvania. Daniel's working with them to improve the way robots get around.
We're working with engineers right now to try to inform them on how they can better design devices, not necessarily that move only through sand, but have to move around on complicated shifting materials. You might imagine a robot that could go into a disaster site where there's rubble and sort of heterogeneous, complicated terrain, might have to encounter sort of ground that can solidify and flow underneath its foot.
For their next experiment, Daniel's team is once again turning to animals to reveal the secrets of granular flow. But this time they're going to need protective gear, not because the animal is dangerous, it's a small lizard. It's because there's an X-ray hazard.
A sandfish is a little lizard, and within a half a second they can vanish beneath the surface of the sand if you startle them or if they're trying to get away from you. And we study these animals by a combination of filming them when they're running around on the surface of the sand with regular high-speed video, and then we also use X-ray high-speed video to visualize the motion within the granular material. We've discovered that these animals vary in a very rapid way within a half a second. And then once they're in the material, they don't run like a lizard, but they start to undulate their body, sort of like an eel. And they can swim for many body lengths in this undulatory way.
There's still a lot of work to be done before the physics of granular flow is thoroughly understood, but researchers are getting there, one step at a time.